Hello, I'm Vladan Stojnić and I will present our work on training ensembles with Inliers and Outliers for semi-supervised active learning. This is joint work with Zakaria, Laskar and Giorgos Tolias. Let's start with defining the task of active learning. Given some labeled data set, we can train a model using supervised learning. Active learning aims to acquire a subset of an unlabeled dataset that will be most beneficial for improving the model's performance if annotated and added to the existing training set. We consider the setup where the unlabeled dataset additionally contains images that don't belong to the classes of interest. We refer to these images as outliers. This setup is more realistic than the one without outliers, which is usually studied in active learning. Here's some useful terms. Outlier ratio is the ratio of outliers in the unlabeled dataset. Acquisition budget is the size of the acquired set, and inlier rate is the percentage of inliers in the acquired set. After acquiring new images, they are annotated and the labeled set is updated. This process can be repeated many times. During testing and evaluation, we are only interested in classifying images into the inlier classes, that is, dog breeds in this example. If we have k inlier classes, that means we need a k-way classifier. Nevertheless, we consider training a k+1 way classifier instead, which additionally includes the outlier class that consists of cats in this example. We refer to this choice as joint training with inliers and outliers. The alternative case is to perform training after discarding all examples annotated as an outlier. The advantage of the joint training is that it enables filtering out outliers from the unlabeled dataset before the acquisition stage. This is achieved by using the trained model to pseudo-label the whole unlabeled dataset. After this, all images that are pseudo-labeled as outliers are discarded before acquisition. Acquisition function is responsible for picking the examples that are valuable for annotation. Several functions exist in the literature. Here are the ones we consider in this work. Random sampling has surprisingly shown competitive results in outlier-free setup. Another way is to pick examples for which the model has predictions of low confidence. A measure of confidence is entropy. Here, each unlabeled example is passed through the model to obtain the probability estimates of each class, and the samples with the highest entropy are acquired. Another measure of confidence is the variance ratio. In this case, each unlabeled example is passed through an ensemble of independently trained models to obtain probability estimates by each model. These estimates are then averaged to obtain the probability estimate of the whole ensemble. Given these estimates, predictions are calculated. The samples with the highest disagreement between separate model and ensemble predictions are acquired. Another way of acquisition is to select the examples that cover the highest portion of the representation space of the model. An example of this is the corset acquisition function. Given the unlabeled dataset, corset first extracts the feature representations from the model. These feature representations can be seen as points in high-dimensional space. The acquisition is then performed so that selected samples maximize the coverage of the feature space. All these acquisition functions were originally proposed for the outlier-free setup and were assumed to fail in presence of outliers by the previous works. The definition of active learning considers access to an unlabeled dataset. Therefore, it is natural to use unlabeled examples through semi-supervised learning. We perform this by first training the model in a supervised manner, and before acquisition, we pseudo-label the unlabeled dataset, and then further train the model using labeled and pseudo-labeled data. This has been previously done in outlier-free active learning, but we are the first to consider it in the presence of outliers. It is important to note that this can only work if we use joint training and k+1 way classifier. A pseudo-labeling would not work well with a k-way classifier. Our full method uses an ensemble of models to perform the acquisition using variance ratio and to improve the pseudo-labeling. We use only one of the models from the ensemble for the evaluation. This is done so that we can fairly compare with the previous work that doesn't use ensembles and to have fast inference. Nevertheless, using the ensemble, which is already available for inference 2, further boost the performance. Our contributions are as follows. We demonstrate the effectiveness of joint training with inliers and outliers, enabling the use of standard acquisition functions that were previously deemed ineffective in the presence of outliers. We introduce the use of semi-supervision as a key ingredient for achieving high performance, which is first application of this technique in the context of outlier-inclusive scenarios. Our approach incorporates ensembles during training only, resulting in a significant performance boost without compromising test time complexity. The key components of this work are theoretically compatible with existing approaches. The practical performance benefits of their combination are empirically demonstrated in our experiments. First, we present the influence of using a k-way versus k+1-way classifier. Using a k+1-way classifier significantly improves the performance over the k-way classifier for all acquisition functions besides random. There is no improvement on random, as the random acquisition is independent of the model. To a largest extent, this is attributed to the significant increase of the inlier rate shown at the bottom of the slide. Because of this, we opt for using a k+1-way classifier in our method. Next, we analyze the necessity of the outlier filtering before the acquisition. We see that outlier filtering significantly improves the results for the random acquisition and much less for others. For entropy and coarse set acquisition, there is an improvement from outlier filtering, while for variance ratio acquisition, there is no difference between filtering and no filtering. Therefore, outlier filtering is a beneficial component. Next, we investigate the importance of using ensembles. Using ensembles significantly improves the pseudo-label accuracy, which then improves classification accuracy over all active learning rounds. Improvement comes even when using a small size of only 3 networks in the ensemble, while using a larger number of models in the ensemble significantly impacts the classification accuracy only for a small number of active learning rounds. Our method uses an ensemble with 5 models to lower the training complexity and the experimentation time. We now present a comparison of our method with state-of-the-art methods for active learning. We see that on a 50% outlier ratio, our method significantly outperforms all competitors, and even a version of our method that doesn't use semi-supervision is better than the others. It is worth noting that similar CCAL, LFOSA, and MQNet are active learning methods developed for active learning in the presence of outliers, while random and badge were proposed for outlier-free active learning. Additionally, our method is the top performing even on the setup with the outlier ratio of 20%. In contrast, all other methods perform similarly to random in this case. We are the top performing even on the higher outlier ratio of 80%, and the second best is again our method without semi-supervision. The top competitor in all outlier ratios is similar. However, it is worth noting that similar performs acquisition by solving a computationally and memory-heavy optimization problem. An important thing to note is that having a high inlier rate during acquisition is not the only determining factor for high classification accuracy. LFOSA has the highest inlier rate in all active learning ratios, while its performance could be better. On the other hand, the 2 best approaches, ours and similar, have moderately high inlier rates. Finally, we showed that our key components, namely joint training with k+1-way classifier, semi-supervision, and using ensembles, can be used to improve other methods as well. To summarize, we have demonstrated that our key components, namely joint training with inliers and outliers, semi-supervision, and ensembles, allow standard active learning acquisition functions to surpass state-of-the-art performance in presence of outliers. Previously, these classical methods were considered to fail in presence of outliers. We saw that these 3 components can also be used to improve other state-of-the-art methods that were specifically developed for active learning in presence of outliers. Thank you.